Hi there, welcome back to the channel. Welcome to the fourth video in the Back to Basics series on tube radio restorations. In this video, I'm going to take you through the audio power stage that makes everything work. This is what you need. Once you've got power, you need audio. Otherwise, you can have as much radio reception as you want. If you can't hear it, it's worthless, right? I'll explain to you the details on the schematic, why certain things are designed the way they are, and also what to look out for, what to replace, what to check. And I want to get to the end of this having communicated, I hope, a good understanding on how the power section of the radio works. There's still a lot to do after that, but we'll take this one step at a time. So whether you're new in the hobby and you want to learn the basics, or whether you've been doing this for some time, you just want to see how somebody else does it, maybe even criticize the way they do it, that's what comments are for, stick around and enjoy the video. But before I carry on, I just want to thank the sponsors of this video, PCBWay. They're the guys I go to for all my PC boards and lately for quite a bit more 3D printing than I was expecting. The results have been phenomenal. Very happy with the turnaround times. As you can see, prices are exceptionally good. They're actually running a design competition, which is the KiCad open source design contest. If you follow the links in the website, take you to the competition page. You'll see the rules, submissions, discussion, and so on. As you can see, it's around two main themes, the communications project or an automation project, and then the awards, the prizes are also listed on here. So whether you're looking for PCBs, 3D printing, or even just going to the store and see what some of the great kits and modules you can buy from them, I'm sure you'll find something for your needs. Well, we've done the initial checks on the power supply lines, the B+ lines, the ones that can go really dramatically bang, but we haven't really got anything working yet, have we? We've got some theory, we've got a lot of theory, we've got a lot of drawings, a lot of color on this schematic, but is this thing working? And how do we test it? How are we going to go into this and test it? Let me tell you my philosophy on this, if you can call it a philosophy. It's just my go-to method, my routine. What I do first is the power supply, as I've shown you so far. And as I said, we have not tested it yet. We haven't put power to this thing yet. We're talking about checking things as safely as possible. The next stage of restoring the radio for me is to make sure that this thing works as an amplifier first. Now, why is that? Well, if you don't have power, you've got nothing. If you've got power and you've got no radio and no amplifier, no audio, what exactly do you have? Let's say you have power and your FM and your AM sections are working perfectly, but your audio amplifier is doing nothing, then you've got nothing. So I like to go backwards in a logical progression. Power, audio, and then the radio sections. And then we've got a lot of little stuff to do. But this is what I'm going to show you next. I'm going to focus only on the audio amplifier. I want to explain to you what needs to be checked. And I also want to explain to you what some of the confusion on that schematic actually does, because there's an enormous amount of stuff that's on the schematic that is really got to do with tone shaping. Now get used to this term, tone shaping. You're going to hear it a lot. It's getting the tone optimized, if you want to call it that. This thing was extremely expensive in those days. I mean, these things would cost you probably a couple of months' salaries, not like today where you just buy it and discard it. So these things were made to give you some really, really good sound. You know, they wanted to allow you to tune this thing with the right treble level, the right bass level. They wanted this thing to sound great at high volumes. They wanted it to sound good at low volumes. It had to do with the type of speaker it was using, the type of enclosure. So there was a lot of tone shaping that went on in here. And the way they implemented tone shaping is very interesting, and I want to show you that on the schematics. I'll go through that in quite a bit of detail, which you can skip ahead if you don't like. But ultimately what we're talking about now is getting to the next stage, which involves two tubes. That's it. The audio amp and preamp stage involves two tubes, and one of them is actually doing double or triple duty. The first tube we're going to talk about is this one. It's a 9-pin power tube. This one's the EL84. There are many, many, many radios from this area that use this tube. It was very, very popular, which makes it very abundant today. The prices have obviously gone up, but it is still pretty abundant, easy to get replacements for. In fact, they're making new ones nowadays because a lot of guitar amps use this, and there's a big market for guitar amplifiers. So this one is the power tube, and it goes in here. And the second tube that we're going to look at today and test the circuitry around of is this EABC80. There are 3 diodes in here and 1 triode. Now, as far as the audio is concerned, we're only interested in the triode, so we'll ignore the diodes for now, but that goes in there. And what you're looking at there, those two tubes, comprises the full audio section of this radio. This does preamp work, this does power amp work, the output transformers over there, it feeds the speakers. Obviously there's a lot of stuff involved that gets the audio cleaned up and to the condition that allows this to amplify it, and we will be looking at that, but that is it. Without these guys, you get absolutely nothing coming out of the radio. You might see a couple of little dial lamps going on and it'll look cute, but it won't produce any sound. If you break this down to its essentials, the audio section is actually quite simple. It takes audio from various sources, it preamplifies it, amplifies it, and sends it out to your speakers. Now, you've got various audio sources, as we've seen before. One of them is the pickup here, which takes your signal from the socket at the back from your gramophone or a tape input. That is your TA. If you press FM, you are directing the signal from the FM section through the audio stage. Then you've got the AM, and the AM has two distinctive sources, but in the selector switch, it's only one. So it's medium wave or short wave. They go through the same routing, and you can see the little diagram there. Let's call that A, let's call that B, let's call that C. Now, once it gets through that then is fed through to the volume control, and this is our volume control here, and that'll set the level of the signal that you want to go through, but it is still a very low level signal, which then gets fed to the preamplification stage, which in this case is the triode within this particular tube. It's a simple triode amplifier. There's really not that much to it. It just preamplifies the signal, right? It takes that signal then to the power stage. Now, between this stage and that stage, between the preamp and the power stage, there is a fair amount of tone shaping. Now, what is tone shaping? Well, it could be as simple as controlling the amount of bass that you want to hear in your signal. There's your bass control, or the amount of treble that you want your signal to have. So there's your treble control. And it also has a separate bass button here. When you press that, it gives you overall more bass anyway. Now, that's a part of the tone shaping, or these three are parts of the tone shaping that happen between the preamp and the power amp stage. But there's one further element of tone shaping that happens on these radios. And that is actually after the power stage, after the power transformer, and actually from the speaker itself. There is a feedback network from the speaker itself that sends a part of the output signal, a small part of the output signal, back to the preamplification stage, which really adds or subtracts certain frequencies that you're getting at this end to the signal there to then either increase it or decrease it. Usually it's a negative feedback, so it'll subtract certain frequencies, and the amount that happens there is sometimes selected by the various buttons that you have on the radio. And this thing has got those buttons at the top. You know, it's got jazz, orchestra, speech, and so on. When you press those, it will cut out certain parts of the frequency band to shape the amount of either bass or treble that you allow through. We'll go into that in a lot of detail when I look at the schematic, but for now, that is the basic breakdown or flowchart of the audio signal going through the radio. We have the audio selector, we have the volume control, we have the preamp, we have the power amp, and we have tone shaping in the form of these controls, that control, and also that little band of switches that the presets that you have in front of the radio, which is the one that plugs into there, which is now stuck to the cabinet itself for now. But that is our audio stage. Now that seems pretty simple until you look at the schematic. So here we are. We've got the schematic again, and I'm going to do the usual. I'm going to show only the audio section like that. So this is our entire audio section. Now compare this to the little block diagram I gave you. It looks a little bit more complex, but it's actually not that difficult to understand. And I'm going to show you what a textbook power amplifier stage looks like, so we can compare this and see if we've got a correlation between them. On the left here, we've got a textbook pentode power stage. Now, this is the sort of thing you'll find on even Wikipedia. It's the simplest version of this schematic that you'll probably find. And we have got our system over here. Now, it looks a little bit different, doesn't it? Looks quite different, actually. But if I take it one step further, I've deleted a lot of stuff there's two things I need to show on here, which is the B1 plus and the B2 plus over here, there and there. We can hide more things. The first thing we'll see here is we've got a lot of speakers on here, which is a little bit strange. On here, we don't even have a speaker, but the speaker would go between those two lines over there. So if we hide the extra speakers on here that we don't have in our system, or we don't need to worry about to look at the theory of this, it becomes a lot easier to understand, like that. All we've got now is one main speaker, and we've actually still got the electrostatic tweeters over here, which for the purpose of describing this circuit, correlation to that, we can hide that as well. And I want to hide everything that doesn't have to do with the direct audio input to the preamp and the power amp stage. That makes this a hell of a lot easier to understand. Okay, now, what are we looking at here? Well, we have got a EL84 power pentoden here. We've got our output transformer here. There's our speaker. There's our B plus coming in, B2 plus coming in. We've got the triode part of this EABC80. That's that little section at the top there. That's what interests us. There's actually a little bit of stuff here that I cannot eliminate or cannot sort of hide because it's in the direct path of the signal, but it'll be easy enough to understand. But essentially, I want to look at this section first and correspond it to that. What do we have on here? We've got our secondary of the output transformer, and there it is there. We've got the primary of the output transformer, and that is it there. We've got B plus up here coming into the primary of the output transformer to the anode of that tube, and there it is here. There, you see, B plus goes into the primary, through the primary, to the anode of the tube, which is pin 7. That's exactly the same, right? We've also got B2 plus, which goes to the screen grid, that second grid in the middle there. There's our B2 plus, which goes straight to the screen grid. Over here, what we've got is from the B1 plus, this is B1 plus, we've got a resistor, a smoothing capacitor, and it gives us our screen grid voltage, G2. It looks slightly different, but it is actually the same as what we have on here. If you recall, the B1 plus went through there, came through there. Let me show you. Part of it's already hidden, but it goes through there. It goes through that resistor there, and then it becomes B2 plus because it meets that capacitor there as well. So we have exactly the same thing. It's going to the grid there as well. And of course, it then goes on to power the preamp stage and the other stages, which we don't see over here. But that would do the same thing from that point onwards. Now, what we've got depicted here is one tube with the anode connected to the primary. The grid 2 is that screen grid over there. We've got the cathode through a resistor and a parallel capacitor to ground. That's exactly what we have here. There's our cathode, there's our resistor, and a capacitor to ground. Now, this is to create what is called cathode bias. I'll explain that in a second, but we see the exact correlation between these two components here to there, okay? If we follow the grid there, we go back to here, we've got that resistor there, R146. That is that guy there, that's a grid stopper. And then just before that, we've got a resistor to ground, R19 over here. And that is that resistor there. You see, there's the grid stopper, and then it meets that resistor, it goes to ground. Ignore this for now. That is our grid leak resistor, which we have over here as well. Then we've got, coming in there, we've got a signal which looks like an audio signal, but there's a blocking capacitor here. This is a DC blocking capacitor, and you'll see in a second why that's necessary. But where is it on our circuit? Well, ignore this part here. This is actually a tone shaping element, which I didn't want to hide because I didn't want to hide the essentials of the circuit. If you consider this to be a straight path through there, and it goes through there, and it's basically a straight path through there. Follow that top line over there. We'll see this in the tone shaping, but it comes to here, and then we've got this capacitor. So this capacitor is that one there, and it blocks DC from this section to that section. Why would it do that? Well, if you look at this tube here, this anode, this is the output of the preamp tube. This is where the signal preamplified comes out and is going to be fed into the power stage, okay? Now that thing there tells us, the schematic tells us, that that can be at 55 volts. Now if we have 55 volts there and we didn't have this blocking capacitor, what would happen? 55 volts would go straight through there, straight through there, straight through there, and it would go to the grid. We can't have that. Now, I just wanted to explain how this schematic correlates to our schematic, but next I want to show you how this thing works. What we have here is the transfer characteristics for the EL84 tube. This one comes from the JJ catalog, and the most important graph we have is this one here on the left for our purposes for this short description. So let's focus on this for now. This gives us two lines. One of them is when the anode voltage and the screen grid voltage are identical, and that's not what we have. What we have is screen grid voltage slightly lower than the anode voltage, which is our case. So we're going to look at number 2, line number 2 over here. They're not the same voltages, but they're good enough for the explanation I want to give you here. So we're looking at this second curve. What does this tell us? Well, it tells us what the anode voltage, IA in milliamps, is in relation to the grid voltage. Now, when you say grid voltage, what they actually mean is the grid to cathode voltage. In other words, the grid voltage relative to the cathode of the tube, okay? Not relative to ground. I'll show you that in the other drawing in a minute. But what it tells us is that if that voltage is 0 over here, look at our current. It's way up there, 120, 128 milliamps. That's going to blow the tube, probably blow the output transformer as well. So we want this current to be lower. And how do we make it lower? Well, our tube is like a tap. Yeah, it's like a tap, and you can't leave it fully open, which is what happens when you've got 0 volts on there. You've got to start squeezing, and the way you squeeze it is by putting negative voltage on the grid relative to the cathode, to the point where you sort of bring it down that curve to a point which is sort of controllable, you know, here, thereabouts, okay? And why do I point to this position here? Well, we know from our schematic that our grid voltage is actually, or cathode voltage is actually 6.8 volts, right? 6.8 volts. That's our cathode voltage. We're talking about the grid voltage. What the hell's going on here? Well, to see that, we've got to go back to the drawing here. And this is where it gets interesting. To bias a tube, you either make that ground and make that negative, or if you can't do that, like in this case, we don't have negative voltages on here really, you make that 0 and you make that positive. It's the same thing, right? Think about it. What you want is V grid to cathode to be negative. So the grid to cathode to be negative means that that is 0 and that's negative, or that is 0 and that's positive. Okay? We're told that we have 6.8 volts on here. Now look at that. How do we get 6.8 volts here? Well, there's a current flowing through this as soon as this switches on. The current flows through here. It flows through this resistor, which I happen to know is 180 ohms. And the current flows through here, and it makes a positive voltage there, creates a positive voltage there. Ohm's law, right? It happens to be like 30, I think it's 36 milliamps through 180 ohms gives you 6.8 volts, okay? That current is creating that voltage, but that guy there, as it is here, is at 0 volts. Now, why is this thing at 0 volts? Well, this is where the high impedance characteristic of a tube comes in. We say that a tube is high impedance because it effectively doesn't draw current into the grid. You know, a few electrons escape, but let's call it 0 current. What happens when you have 0 current across a resistor? You have 0 volt drop. And look at this resistor here. This is at 0 volts. If there's 0 current flowing in there, there's 0 current flowing through here, which means that this is at 0 volts. If that's at 0 volts and there's 0 current flowing through that resistor, it means that's at 0 volts. So our V grid to cathode is 0 minus 6.8, which equals minus 6.8. So we've got a negative bias voltage, grid to cathode, because of that resistor there. That's the cathode resistor that's creating the bias point. And that is creating, because of this condition, it has closed off some of the current path through here. It's stopped this inrush of current that just wants to flow through there like a big hose pipe with no restriction at all. You've taken this huge hose pipe and you've gone, you know, you give it at minus 6.8. Now not much current or water can flow through, right? Now you've blocked this to the point where it's got its steady state of 36 or 35 milliamps, whatever it is, right? You can bias it more or less by changing that resistor there and a few other things. We're looking at this in a simplistic form. Big hose pipe, lots of water flows through. You want to control it, so you squeeze it. Okay? And you squeezed it by applying that negative voltage. Now look at this again. We've got 6.8. There's -5, -6, -7. There's our 6.8. Okay? Which means it hits the graph sort of there. And if it hits the graph there, look at our steady state current. That is it there. 20, 1, 2, 3, 4, 5. So that's about 5 each, right? 0, 5, 10, 15, 20. No, it's 4 each. So 20, 24, 28, 32 milliamps. That's what this chart tells us. 32 milliamps. This calculation over here gives us 36 milliamps. Not bad. Not bad at all. Pretty close. Okay? Now, we've got this tube under control. It's not going to run away with us. What do we do next? This is supposed to be a tube. This is supposed to amplify a signal. Now, don't forget that we have to differentiate between DC and AC. These are the DC conditions. DC voltages, 0 DC volts, 6.8 DC volts, 280 whatever DC volts, okay? Current is flowing through there, steady state, no signal because there's no alternation, no alteration. It's a steady situation here. There's no signal coming out here, right? This only induces a signal on the output to the speaker when there's a changing current here, right? Just as a resistor would give you a changing voltage, this transformer will induce only when there's a change, because transformers, they only induce alternating magnetic fields to the second coil, the secondary coil, with AC conditions, with altering conditions, not with fixed conditions, okay? Right. Now, what happens when you put let's call this an AC signal over here? And let us say that this AC signal is 2 volts peak to peak. So that's plus 1 volts, and that there's minus 1 volts. All right? What's going to happen here? Well, if you look at it at the point when this hits the top of that wave, right? It goes up to 1, comes down to -1, goes back to 0. When it hits the top of that wave, that's going straight through that capacitor, because the capacitor will allow AC to go through, right? So suddenly, this voltage here, this increase in voltage, will make that higher. It'll make that increase as well, right? That'll increase to plus 1 volts. Now, if that goes up to plus 1 volts, it's going in a sinusoidal fashion, but when it hits plus 1 volts, that thing there, this voltage is now different. This is now no longer 0 minus 6.8, it's 1 minus 6.8, which means that is minus 5.8. That there will be minus 5.8. What's going to happen to the current through there? Well, we'll see. We have gone to minus 5.8. Now 5.8 is over here, right? So if we follow this till we hit the line, we're now there. What current are we going to get through the anode? We are going to get 44 milliamps. That's the current over there. 44 milliamps flows through the anode now. But the signal starts coming down, right? It starts coming down, gets back to 0, and then it starts going negative. When it goes negative, it's getting to the point where that's -1. Now, if that's -1, that voltage there, that instantaneous voltage there will be -1 as well. That's -1. So what happens? That's -1, that's 6.8. The difference now is -7.8, right? -1 minus 6.8 is -7.8. What happens to the current through the tube then? Well, if we look at over here, -7.8, that was -6.8. That's -7.8. At -7.8, about there, look at the current. The current is now 22 milliamps. So the current has dropped. So what we're getting here is we're getting our current alternating between 20 milliamps and 44 milliamps, sort of depending on the signal that's coming in. This thing here is modulating the current through there. When this goes up, the voltage, the grid to cathode voltage drops, which means the current increases. When this goes down, the grid to cathode voltage increases, so the current decreases. Now, because it's inducing, this current is passing through that inductor, that primary, what's happening is when this goes up, This is the signal we're going to see at this point here. It's going to go down. When it hits the bottom, it's going to go up. When it gets to there, it's back to normal. When it goes negative down here, and it does that. This is our signal that results from that input. This is our output across, this is the signal across the output transformer that input signal induces by controlling the current that's flowing through here. And that current in turn alternates or modulates the magnetic field across the primary or created by the primary, which then induces a signal on the secondary. That's as simple as it gets. And you can get this from hundreds of little tutorials and explanations on the net. Any book on tubes and how they work, there are thousands of references, probably explained a lot better than I can do. So I would really recommend you do some reading. It's really interesting stuff. And once you click, this is the beauty of this stuff. Once you click, you never forget it because it makes sense. I was always taught that you don't try to remember things. You try to learn things, understand things, because if you understand things, you can sort of build up the argument to the point where you know what the answer is. If you just try to remember, you forget the answer, right? Or you mix it up with another answer. That's how the output section works on this radio. And what does that mean to us? Well, other than telling us how this works, we can now start checking that this tube is safe to switch on. Now, why do I say safe? Well, remember we're talking about this here being 0 volts. More or less, based on 0, relative to that, right? Well, actually relative to ground in this case. What happens if suddenly this goes up to 50 volts? Over here, this point here. If that shoots up to 50 volts, this thing is going to just blow up, right? It's going to blow up because this thing's going to open wide open, right? There's going to be positive voltage, not negative voltage. This tube is just going to blow up. It's probably going to blow out the transformer, burn out the primary, that secondary, the output transformer first. And the reason this can happen is if this capacitor here doesn't do its job. If this starts leaking DC voltage, that becomes positive because here on this side, you've got high voltages. You can get voltages as high as 150 volts. In our radio, I think it says 55, if I'm not mistaken. But if that 55 is allowed to go through, other than that audio signal, which is probably a few volts peak to peak, that becomes voltage, that becomes positive, and that whole stability that we've created here just goes out the window. And that's when you get runaway. And the reason I'm explaining all this before switching the radio on is because we have to check this capacitor first. That is the one that can blow up our system. Because if it's leaking, it means we're going to have our output tube under stress the minute we put power to that radio. Okay, let's start checking this. We're going to check this resistor first down here. So it's from pin 3 of the EL84 to ground. We expect 180 ohms. We're on the top, so we count the pins counterclockwise. So that's 1, 2, 3. Ground is anywhere on the chassis. 179, 179.4. That is perfect, perfect. Now we also have a capacitor to ground over there, this guy over here. So that goes from pin 3 to the positive of the capacitor. It's 100 microfarads to ground. I always replace those. I just want to see which one it is. I think it's that guy there. So 1, 2, 3, let's see if that's the pin. Yep, that's it, and that should be ground. Yep, that's it. So the resistor is fine. That capacitor is going to be changed. And that capacitor is actually quite easily reachable. There's the positive, there's the ground. Let's see if we can do this on camera. Just clean up the pads. Two things I don't skimp on. Well, two of the things I do not skimp on is the solder braid that I use is from Chemiwick. Costs about 3 times more than the cheapest stuff, but it is fantastic. And the other thing is this guy. This is a solder sucker called an Engineer solder sucker. It's fantastic. It really works well, much better than all the others I've had. So I swear by it now. Now this is the capacitor I'm putting in here. It's 100 microfarads, 50 volts, so a bit overrated, but it's going to do. And I've got a problem. The legs don't reach. Ah, damn it. All right, I've got to put an extension on that guy. Actually, I don't need to put an extension because they've very thoughtfully created 3 holes on the ground. There's the positive, goes to there. That's got to be in the same place every time. I bent the wire in, I bent the lead, make sure it's nice and firm. And then they've given us 3 negative holes, 3 holes on the ground, 1, 2, 3. So you can sort of use different size lead-spaced capacitors, and this one fits perfectly here. That's a good ground connection, I think. This this is a ground wire, so you've got to give it a bit more heat. Done. All right, we've replaced all of 1 component. Isn't that great? Okay, so we've checked all of 2 components, these 2. And now we're going to carry on. These pins 9 and 7 we checked when we did the B+ follow through. Now we're going to pin 2, and pin 2 goes to that resistor there. It goes to a 100K resistor, which meets a 680K resistor. That's the grid stopper, that's the grid leak. And we are going to check these 2. Now, the way to do that is to go from pin 2 to a 100K resistor, or you can go all the way down to ground, which means that you should measure 100 plus 680, 780. This is a dead end because it's a capacitor for DC. That's open, so we should be able to measure just those 2 in one go. Let's try that. So it's pin 2 to ground, 1, 2, and ground. 810. So we're expecting 680, 680, 780, 780, 880. It's still within spec, but let's just check whether it's the 100K resistor or the 680 that's out. So pin 2, there's a 100K resistor. That's where it goes to it. Yep. And let's measure that. 102, that's within spec. Now let's measure that to ground. The 680 is measuring 40 above 5%. So that's not too bad. That's fine. And that's the junction of those 2 resistors, which we now need to measure. So we know those 2 are fine, but that's the junction of them. And that is where we go back to the schematic. And if you go to the schematic, you see it goes to a potentiometer and a capacitor. Now, this is a, well, what would it be? A base, yeah, this would be the base control. So this junction here has got to go to the base control, and then from the base control, it goes on to that pin 7 of that socket. But let's take it one step at a time. Let's look for this junction on the underside and see where that connection goes to, see if it actually goes to the base control. And I found it. There it is there. It's that guy over there, right? That's the underside of that junction of those 2 resistors, the 100K and the 680K. That red wire is the one that brings the signal back. And this is where it comes to. It comes to one of the legs of this pot. And this pot is actually internally wired as a variable resistor. It doesn't even have the three legs, it's just 2. So what we can do, actually I can check that it comes from there, because if I touch there and I touch the top, there's my multimeter telling me that it's got continuity. Now if I want to check what resistance that is, now remember the pot says, or the schematic says 10 meg. What is actually there? Well, to check that, I put this across those legs. Oh, by the way, you see what that is? That is that 300 picofarad capacitor that's in the schematic. And these are polystyrene, and they usually are perfectly fine. So I very seldom replace them unless there's an issue. Now, let me see what resistance we get on here. That's 149K. Oh, this thing is really going crazy. 25 meg, 42 meg. And it goes all the way down to almost 0, less than 1K, okay? But it goes all the way up. Now, I don't know whether this pot has, it's a logarithmic pot because I'm turning it all the way over. That seems, oh, that's open because my lead is jumping around. Yeah, okay. This thing has gone over, there we go. 9 point something meg. So that part is perfectly fine as well. I think it's actually dirty because there are parts at the top there that seem to be opening up. So I can carry on backwards. And backwards is if you take the other wire that comes to that pot, which is the pot and the capacitor. These are in one down there. And it's the black lead. So it's that lead over there. And this thing tells us that it goes to pin 7. Now, what is this pin 7? Well, this pin 7 is actually on that socket over there. That socket is the one that goes to the top, that you connect that the assembly of tone shaping elements on the front panel. Remember, I was able to just pull it out, and it goes to pin 7, and I can tell that it does go to pin 7 because I can see the wire. I can see the black wire that comes from the bottom here. It goes to there. And that is, there's the gap. And now I'm on the underside, so I go clockwise. 1, 2, 3, 4, 5, 6, 7. That's it there, right? Perfect. But you can also go one step further because we've got pin 7 over here and we've got pin 6. Now this thing goes out and comes back, all right? It goes out. It meets this little circuit, and this will be the speech button or speech selector on the front panel. And then it comes back through pin 6. So if I go to pin 6, I can now find where this capacitor is because I look at what capacitor is connected to pin 6. So if we go back to here, that's pin 7. Pin 6 is this white wire over here. That one over there. Let me just mess with it. It's coming to the top here. And I know the other side of this capacitor is connected to pin 9 of the preamp tube. So that's what I'm going to trace. And this is the capacitor that I call the one that's crucial that you replace or check, at least check. So let's find it. And it's on the top side of the board as well. So we have to go to the other end. So here we are at pin 6, so 1, 2, 3, 4, 5, 6, coming back, and I believe it goes to this one here, which it does. We can hear that. We can hear the beep, the continuity, and the other side of this capacitor goes to should go to pin 9, and 9 is that one there. So this is the capacitor here, and in fact it does say the value that we expect it to say. So I'm going to replace that. Later on we can check just what condition it's in. So I'm looking for a 10 nanofarad. I normally use 630 volt capacitors throughout, and that's what I'm going to replace it with. It's as simple as desoldering the underside, pulling it out, and putting a new cap in there. All right, we've now checked the entire signal path from the output of the preamp tube, or the preamp stage of that tube, to the power stage, to the power tube, and through there. And all we had to do is replace two components. That capacitor there, the coupling cap, and also, of course, this one, the cathode bypass capacitor. And that's all I'm going to do today because I don't want to power this up yet. I suppose I could, because I could feed the signal to there, to the output of that, the preamp, and get it through the speakers. But there are components on here that I want to check that are related to this tube. And when I do power it up, I need these two tubes in place. So, I don't want to risk it. There's one other aspect here I want to talk about. Before I power this up. There's a capacitor here that probably needs changing. For now, I'm going to leave you. I've got two components removed, and quite frankly, I don't know what their condition is. And you know what? I don't really care, but let's just have a quick look and see what condition they are in. For curiosity's sake, if nothing else, here is that coupling capacitor, giving us 12.5 nanofarads. Not bad at all. That's perfectly within spec. What is the electrolytic like? Oh, 220. This is supposed to be 100. That one is kaput. So this one is obviously gone. I'm not even going to check the SR on this thing. This one seems to be in pretty good condition. And it is sort of a more modern style film cap. It's not one of those ugly paper types. So maybe this thing was changed subsequent to the radio being put on the market. I'm not sure. This might have been a replacement. This is definitely a foam cap. I bet you if I test the leakage on this, I'll get no leakage. Let's try this. This is a 630 DC cap. I'm going to try my capacitance leakage test and see what leakage we get out of this thing. I'm going to connect the capacitor to the test leads. And I'm going to be careful where I place this because whatever voltage I apply to the capacitor, it's going to be across those leads, so I don't want to get zapped. Switch it on. It's actually off because it's in the off finish, in the discharge position. I'll leave it on high, drop the voltage before I zap it with anything. Put that in the 100 milliamp position. A little bit of a flick, nothing else. Let's up the voltage. Let's put that on. That's on 10 milliamps, 1 milliamp. There is nothing there, no leakage there at all. Let me put it on the top range, 330 volts, and there is no leakage. Let me put it on the 100 microamp range. Oh man, I can't even see it twitch. This capacitor was in perfect condition. All right. Now, as I said, if I touch that, I'd get zapped. I'd get 330 volts on me. So you've got to be very, very careful. And now I'll just bring this down, and that's in the discharge position. I normally drop this and switch off. Okay. And that's what I'm going to leave you for now, because the next stage requires quite a bit of preparation, a few drawings to give an explanation of how the tone shaping works. Yeah, that's something that is next on the agenda. So I'm going to leave you for now, and I hope you enjoyed this video. And if you do enjoy it, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Links on the description below. Once again, thanks for watching. Bye for now, and most of all, stay safe.